Okay, so yesterday we left off and you calculated all of the velocities of light traveling through these various materials.
Right.
Check and make sure you rounded correctly. Questions on any of those? Okay, so the reason why these are important is because you're going to use these velocities in Snell's law. We'll talk about what that is here in a little bit. To figure out how much your light rays bend when going through these materials. Okay? So, before we can talk about that, we need to talk about reflection. In the lab, which box was this? Law of reflection. It's the first one, yeah. So you set up your ray box to direct your light ray where the mirror and your normal, remember your normal line is perpendicular to your reflection surface. And what you should have found is that your theta I is equal to your theta R. Your angle of incident is equal to your angle of reflection. This is true for any surface. Okay, not just a mirror, but it's true for any surface. That the point at which the ray hits the surface, the reflection ray will be equal in angle in reference to the normal. Now in this particular instance, we're talking about a plane mirror. Okay, not like an airplane, but a plane, plane meaning flat, like in geometry, along the same plane. Okay. All right, moving on. There are three types of reflection. And those types are determined by the object the light is reflecting off of. Is it reflecting off a nice smooth surface? Is it reflecting off a unsmooth surface? Or is it reflecting off of a curved surface? Okay? And depending on what surface it is will determine what type of reflection you actually have. So, types of reflection are what? What are three types of reflection? Okay. What's our first type? Diffuse. What's our second type?
Perfect.
Perfect. And finally, we have focus, right? There's a mirror image.
Wow.
And what did I say? This is determined by these types. The type of object it's the light is reflecting off of. That's right. So if you want an object to be really shiny, for example, a car, you want to make sure that that paint is really, really smooth. So it will reflect that light in a more perfect fashion. So we're first going to talk about perfect, okay? Looking in a mirror. So when you're looking in a mirror, and that is a plane mirror, not a carnival mirror. A plane mirror, you should end up with a perfect reflection. So the first thing is that the distance you are from the mirror is equal to the distance the image appears to be inside the mirror. So, for example, if I'm standing and looking at this window, which is actually like a mirror, right, the distance I'm from that window, which is say about 15 feet, is the same distance that my image is inside my mirror. So it looks about 15 feet inside the mirror. Okay. Also, if you have a perfect reflection, or actually any reflection, the images are going to be inverted. Just like the letters were on that previous slide. So when you look in the mirror, and this is common sense, but you look in the mirror, you're not seeing the back of your head, right? Hopefully.
That'd be crazy.
Why am I looking at two?
Yeah, that's why you need two mirrors to look at the back of your head. Also, the size of the mirror versus the size of the object. Let's talk about that. Now, does this mirror need to be this length to see all of his image? No. Does it need to be his height?
Yes.
No.
No. Doesn't even need to be his height. Because if we look at this, actually see, look at how the light is traveling. So, the light from the top of his head hitting here, bouncing off the mirror, and going to his eyeball, right? Same with his foot. Bouncing off the mirror, going to his eyeball. So the mirror only has to be that big. The same thing if I have this small mirror, this 2-inch mirror. Right. If I hold it close to my eye and look out in the class, I can see this entire section. Right, this mirror is not that big, only 2 inches, but I can see a full, probably 6 by 25 feet, 6 feet by 25 feet section, in 2-inch mirror. Now, if you're looking at the mirror, okay, back at me, all you're seeing is a small section of my face. as I move the mirror further away, okay, I see less. Okay, at this point, I can only see one head.
So, closer you are to the mirror, the more you can see.
Closer you are to the mirror, the more you see. Right? Because that gives the light rays that are bouncing off the mirror time to refract at a larger angle. And so you can see more. So, the area of the mirror does not have to be the same size as the object you're looking at. It all depends on the distance you are away from the mirror.
There's the dot. That's great.
Next, we're going to look at diffuse. So, if an object isn't perfectly smooth, doesn't have a perfectly smooth surface, which is almost everything that we come in encounter with on a day-to-day basis, right? Or else everything would look like mirrors. Okay? Most everything we come in contact with does not have a smooth surface, a perfectly smooth surface. And when I say perfectly smooth, that's all relative, right? Because even if you magnify the surface of a mirror, it's going to be dimpled and pitted out, okay, depending on how close you get. So if I have this green block, okay, and I magnify the surface of that green block, it might look like that. Okay? Just looking at an angle of the surface. And we have all these peaks and valleys. Okay? It is not a smooth surface. So what's going to happen when the light hits?
Going.
It's going to go in all different directions. Remember, the angle the light reflects is based on what? The angle the light reflects is based on what? Okay, but more importantly, go back to the law of reflection. What is the most important part of that? What is your perpendicular line? The normal. Okay? So your light reflects depending on the normal. So look at this section here. Which direction is the normal? Yeah. Going northeast, right? Perpendicular to the surface. So if we look at these light rays, we're going to do that. Okay? So here's our normal. When our light, remember our light's coming all parallel blue lines in a straight line. Once they hit our surface, depends on what the surface looks like. You can almost think of it like a bouncy ball. Okay? If I throw a bouncy ball at the surface, it's going to bounce off at that angle. Right? Same with this light ray. This light ray is hitting the opposite direction, our second ray, and it's bouncing back to the left. So what's going to happen is all this light's going to scatter. It's going to become a diffuse reflection. Questions on that? Okay, let's go back and look at our perfect reflection again. So, when we have our light rays hitting our mirror, and you did this in the lab as well, right? Where are our normal lines? Which direction are they going? North south, right? Because they're perpendicular to the mirror surface. Those are our normal lines. So remember that our angles of our incident, which are the source, will be the same as our reflection. Yes? Maybe you're Everyone have that? Yes? Good. Okay, so let's talk about focused reflection. So we have diffuse, where it scatters. We have perfect. So our law of reflection. Incident is going to equal, or pardon me, our reflective rays are all going to be parallel to each other. Now we have focused. So we have two different lenses. Okay? Our light is going to be coming from the center. The light rays. So, call them all as a group. So, this is in reference to the center. Okay? So this is convex, right? Because it's bowed outwards. Concave, remember caves go in, is our second lens. It's bent inwards. And if you just remember that these reflection is always based off our normal line, and the normal is perpendicular to the surface, then you should have no problems. Devin, you have a question?
Oh, never mind.
So, convex. We get that. Remember, these are not convex lenses, these are convex mirrors. Two different things. Yes?
Does that mean that the two mirrors are facing each other and, like, I guess not whatever the mirror sees, if that makes sense. So what the other one sees, what are you trying to say, or no?
These are two different these are separate. Ignore that that's the concave here for this example.
Okay.
This would be, if you were standing in front of this mirror,
You look bigger?
you would look bigger. Yeah, you'd look really tall. Or
That is.
really fat. Because it would bend that depending on how it's bent. Okay, if it was like a fisheye, if the whole thing was like a sphere, then you'd look big and fat. Okay? Because it would expand the light. It would distort you. What about concave? What's that going to do?
Pretty longer.
Be smaller.
That's right. So it's going to bend the light into the middle. This point here, where they hit, that's your focal point. Okay, everyone drawn that and labeled it? Okay. These are mirrors, not to be confused with lenses. The biggest obstacle is confusing the lenses and the mirrors because they're opposite of each other. So if you don't have them labeled correctly, you go back, you have issues. These are both mirrors. Because we're talking about reflection. If they're lenses, what would we be talking about? Would we be talking about reflection? Refraction. That's right. They'd be reflecting off. They'd be, it's majority. They'd be traveling through. An example of our convex mirror is the side mirror car. So what would be the advantage of this?
You see things better?
You can see more. So you see a wider angle. Okay? So when you're looking in the side mirror, you're actually seeing more of what is to the right or left of your car. And because it distorts it, okay, when you're looking at it, it will distort it, making them look closer.
I think it paints a little close.
That's a
How's that
Photoshop.
look? It looks all really close.
But you can see more to the right. So if you're changing lanes, instead of just being able to see right beside you, you can see more of your blind spot. Concave. Example of a concave mirror would be satellite dish, right? What happens is the signal, they point the dish towards the, wherever the signal's coming from, okay? And it's going to bounce off your dish and hit the receiver, which is the focal point, right? So they need to know what the focal point is, so you get a signal that is clear. Yep,
It's not a mirror.
sure it is.
Doesn't mean that has to be a mirror. You can see yourself.
It is still, I mean, by definition, it is a mirror. Technically, it's not a piece of glass that you can see the reflection in, right?
Is it like what you had up when you see the glass and like that?
It is a reflecting surface. So by that definition, it is a mirror. Okay.
I think that Cardi's weird. I was I'm not against it.
So if we were to look at, what type of lens is this?
That's a comeback.
Convex. And we're looking at the surface, this curved surface. We can see why the light does bend out because of our normal lines. Once again, the normal lines are what determine the angle at which your light rays are going to reflect.